name's Orion, and I'm a mechanical engineer with Greenbound Technologies. And I'm going to talk to you a little bit about high velocity and low velocity aeration floors, specifically looking at pipette grade versus Sparger designs. So this is kind of the rough outline of what I'm going to talk to you about, give a little background information, and then get into some data that we took at the facility. This presentation gets pretty nerdy pretty quickly, so be warned. So this orange pin right here indicates the location of the facility that we're discussing. And as you can see, there's two satellite images, one from 1995, one from 2018. And over the years, a lot of people started popping up where there were just cows. And for our client who was just doing a mass bed composting, this became an issue because the people might not have more sensitive noses, but they're definitely more vocal about it. And essentially it got to a point where they're getting lots of odor complaints and needed to change, otherwise they were risking getting shut down. So they contacted us about 5 years ago to help them with the odor problem. And this was a solution that we proposed to them, and it's the solution that they adopted. So what we have is a reversing aerated static pile composting system. And reversing meaning it goes both positive and negative. Tom did a great job of kind of introducing those concepts. So the cool thing about this facility, and the thing that's really unique, is that it has both pipe at grade and Sparger side by side with all other parameters exactly the same. So that lets us do a really unique comparison of how pipe at grade works when compared to the Sparger system. So what is pipe at grade and what is a Sparger system? Essentially, Spargers, as you can see here, have little risers or little pipes that come up out of the laterals. And then there's these nozzles that are fit onto the top of them. And then the nozzles are embedded in a concrete layer. Whereas pipe at grade is just a lateral, and the lateral's flush with the surface of the concrete. And then you go through and drill little holes into that lateral. So they're pretty much exactly the same. And in this case, as you can see from the CAD images, they look almost exactly the same. The only difference is the geometry that delivers the air into the floor. So this image kind of shows you what we designed. This is looking at the pipe at grade section of the compost pile. There's an exact replica of this design right over here where my mouse is. And that is where the Sparger system is. It looks exactly the same. There's two aeration modules, an aeration module being a blower and all the laterals and headers that are connected to it. And the way that these work is there's a VFD, a variable frequency drive, that is connected to the blower, and that lets us regulate how much air the blower pushes. So these are 17,000 CFM blowers. So at 100% VFD, it would push 17,000 CFM, whereas at 10%, it would push maybe 1,000 or 1,700. And then there's various zones that the blower is connected to. And each of these zones has a damper that opens or closes. And those dampers are individually controlled. So if you want to aerate just one zone, you could do that. You could close all three of these dampers and leave this one open and just aerate this zone here. So as you can see, the Sparger and the pipe at grade are pretty much exactly the same. The only difference is what's highlighted here in the red, and that's that the Sparger system has 132 holes per zone, or sorry, per blower aeration module, and those holes are 7/8 in diameter. Whereas the pipe at grade has 288 that are 5/8 in diameter. Other than that, everything is exactly the same. And one thing that's important to point out is that they're composting yard waste at this facility. And when we do yard waste designs, we typically design for an airflow of 3 CFM per cubic yard. So given that, we wanted to figure out how these two things performed. So we started gathering some data comparing the pipe at grade and the Sparger. And to do that, we did some open floor testing initially where the pile was empty. So it was just the pipe or Spargers that were exposed. The tests were taken in this fashion. So we're getting 6 per lateral. And we took a test at positive 100% blower speed, positive 60% blower speed, negative 100%, and negative 60%. And it's important to note that when we did this test, all the dampers were closed except for the zone of interest. And that's because we were getting this data at an operating facility. So the other zones had compost piles on them, and different compost piles are going to have different amounts of airflow that go through them based off their age, the moisture content, etc. So the only way we could really make a meaningful side-by-side comparison is if we closed everything off except for the zone that we were testing. And to do that, we created this little apparatus here, which is essentially a 3-inch piece of pipe with foam on the bottom that you use as a seal. And you put that over the hole of interest, make sure no air is coming out around the side, and then blow air up through the pipe. And what this does is it takes air that's coming out at really high velocities and just turbulent, and it makes it laminar. So you can get a much more accurate reading. Whereas if you took your anemometer and just put it right over this, you're gonna see huge fluctuations in airspeed. One thing to note is when you do this testing, definitely wear eye protection. I forgot my goggles the first time I went down, so I had to wear these sunglasses. And as you can see, you really get blasted. The air comes out at incredibly high speeds, so it can hurt the eyes. So unfortunately, I can't share all the data, just there's too much, but I broke down a lot of it into various sections looking at averages and the variation. And what we find is that the Sparger floor has an average airflow of 21,000 feet per minute, where the pipette grade has 17,000. These are some super high velocities. And what that means is that given the way they have done, our clients done the pipette grade, it's not really a low velocity system. So what we're really looking at here is not high velocity versus low velocity. We're comparing a Sparger design with a pipette grade design. Another thing I'd like to point out here is that the variance for the Sparger and the pipette grade was pretty comparable. We're seeing 9% variance for the Sparger and 15% for the pipette grade, pretty similar. And that the difference in positive and negative was actually pretty comparable, which is unusual because typically pipette grade performs better in negative than the Sparger. There's some reasons for that I'll get into later. So when you convert that data to CFM, what we find is that we're getting 8.2 CFM per cubic yard with the Sparger system and 7.6. And that's way higher than the 3 CFM per cubic yard that we designed for. And the reason for that is most likely because when we were doing this testing, we only had that one zone open instead of having all 4 of them open, which is what we designed for. So you're going to see a much higher airflow because of that. So after we did that, we wanted to see how air moved through the piles when there was actually compost on them. So we did that by looking at oxygen data and doing these hood tests. And the hood tests look a little bit like this. We built this 4x4 square, and then we had it kind of pyramid up to an 1.5 inch pipe. And what that does is it increases the velocity of the air coming out of the pile as the diameter gets smaller and smaller. So there's velocities that are way too low up on the top of the pile to actually read. So as you come up here and shrink it down to an 1.5 inches, you typically see velocities that are high enough to actually get a reading on. And we took these readings at the places where these red X's are. So we would place the hood there, leave it for a minute, and then record the data. And then we put an oxygen probe in there and record the data. So these are the results. Really what I want to point out here is that the oxygen and the airspeed through the hood was pretty similar, and that unfortunately we weren't able to get a complete data set because it is an operational facility. So halfway through testing, things changed a little bit and we weren't able to get some data on one of the aeration zones. However, there is enough data that we can make some comparisons. And one thing to point out, just looking at this, zones 1 through 8 are pipette grade, where 9 through 16 are the Spargers. And as you can see, there's actually quite a bit more consistent airflow on the pipette grade, whereas with the Spargers, we're seeing a lot of areas where we're not really getting any airflow. And what this most likely is nozzles getting clogged up. So that's something to note. We also have some age data for the piles and biocover data. We're gonna look at that later as well. So looking at this and looking at some averages, what we find is that the variance, which is kind of the consistency of the airflow data for the Sparger system, is around 40%, where the pipette grade is 80%. So twice as much variance, which means there's probably about twice as much clogging happening. And then when we take that data and convert it to CFM per cubic yard, we're seeing a value of 3.4 for the Spargers and 2.6 for the pipette grade. Pretty similar values and also much closer to what we designed for. And then the thing to note with this oxygen data is that we're also seeing much higher variance. So 5 times the amount of variance for the pipette grade as the Sparger system, which also implies clogging. So the last test that we did was header testing. And here's Jeff Gage, one of my coworkers and mentors, riding on top of a header, getting some data. And essentially how we do this is we take an anemometer and we stick it through a little 3/4 inch hole at the header. And we do that for each of these headers at various blower speeds and damper positions. Here are the results of the data. The orange area indicates a space where we couldn't get data because that aeration module wasn't going in negative. They're still doing some construction at the facility and this one wasn't ready to go in negative yet. The thing that I'd like to point out from this is a lot of data, I know, and I'm moving pretty quickly, but the thing I'd like to point out is that, again, much higher variance for the pipette grade. So this validates what we are seeing with the hood and oxygen testing, that there's more consistent airflow when you're using a Sparger system versus a pipette grade, like almost 3 to 4 times more consistent. So when you take this data and then you look at, convert it to CFM per cubic yard, what we are finding is there's actually much lower airflows. A CFM per cubic yard with a Sparger system of 1 and 1.5 for the pipette grade. And this is kind of curious because it's considerably lower than what we were seeing with the hood. And it's also different in that the pipette grade is a larger number than the Sparger. And the reason that this is happening is that when we were taking the data, zone 1 was brand new zone. We just cleared all the nozzles and put fresh compost on, or sorry, not compost, yard waste onto that zone. And as such, it's getting a much higher airflow. You can see here 2,700, whereas the zone right next to it is seeing only 300. So that really goes to show how much of a difference having a unclogged zone makes when it comes to airflow. So that's kind of quickly went through the data. Now I'm going to do some quick analysis to talk about how valid this data and what kind of conclusions we can draw from it. The first thing I looked at was repeatability. And how I did this was basically we did hood testing. I was hoping to do it twice for the whole system, but we ran into some hiccups gathering data. So I was only actually able to repeat this section of data twice. However, the results were pretty promising. It is a limited data set, only 6 readings, but they were incredibly similar, only a 6% variation. So that shows that the quality of the hood readings was probably pretty good. And these 2 data sets were taken 1 day apart. So settling, et cetera, should not have played a huge factor. And then I wanted to look at the consistency of the findings. So was our header data validating what we were seeing with the hood airflow and with our percent oxygen? So what I've done here is created a conditional formatting with the different values. Darker numbers represent higher airflows or higher percent oxygens, and lower numbers are represented in the whiter cells, the less green cells. So as you can see, this is looking at the Sparger system, zones 1 through 8. There's a lot of overlap between the hood readings and the oxygen. So we're seeing kind of not a lot of airflow through here, and we're seeing lower oxygen readings. And then when you look at the header, unfortunately, I couldn't get any oxygen data for zone 1. But when you look at the header, it also kind of makes sense. There's good airflow here through the header, good oxygen, and that's also reflected on this side. And then I also did the same thing with the Sparger system. We didn't have data, again, unfortunately, for the farthest out sample for the Sparger system, but what you can see here is that there's pretty good correlation. Lower airflow here, lower oxygen, higher airflow through the header here, higher hood readings, and oxygen percentages. So things are looking pretty consistent. So when we look at the airflow through the systems, the pipette grade versus the Sparger, what we find is that it's actually pretty similar. Regardless of what kind of test we get, the values for pipette grade versus Sparger are proximal to one another. For instance, with the hood, we're seeing 3.4 CFM per cubic yard, and the pipette grade, we're seeing 2.6. So those are in the same ballpark. Same with the header, 1.0 versus 1.5. There are some differences there, and I have some theories, but I can talk to anyone who's interested about that later. And the other thing that was really staggering about this data is that the air distribution was 2.5 times more consistent through the Spargers. So you're looking at this variance, and the variance is 2.5 times lower for the Spargers than the pipette grade for airflow, and 5 times lower when it comes to oxygen. So we're seeing much more consistent airflow for the Spargers. The next thing I want to look at is if age or biocover were having a substantial effect on airflow. And essentially, long story short, I analyzed this data and was seeing that there is some relationship between biocover and airflow and percent oxygen. And there's even more correlation between age and airflow and percent oxygen. The interesting thing is, though, both biocover and age are also correlated. So, for instance, the fresh piles would not have biocover on them, and they're also the youngest. So to figure out which of these two is affecting the airflow, I did a little bit of analysis and turned towards this Burke-Plumer equation, which was for turbulent flow because the air flows are really high. And this is essentially an equation for looking at the pressure drop through a porous media, which compost is a porous media. And what I did was changed the L value or the depth value for two different readings. One I was assuming was 13 feet deep and didn't have any biocover, and one's 14 feet. And I'm assuming all the other terms are the same just to get some quick data and make this simple. And so I can divide everything out. And when you do that, we find that when you increase the depth by a foot or add a foot of biocover, we're seeing a 7% greater pressure drop through the media. So it's not super significant. And then I wanted to look at the effect of age. And really, it's not the age of compost that's causing the airflow to reduce. It's the settling of compost in time. And JT Van Ginkel et al. Did some interesting research on the effects of settling in a hay chicken manure pile. Obviously, that's a different feedstock than the yard waste that we're looking at here. But what they found was that there's an average of 20% settling per week, 16% of which was subsidence, so volume loss, and 4% was mass loss. So we're going to estimate, for the sake of this, just conservatively, that there's a 10% reduction in porosity for the first 2 weeks. And we're going to look at how that affects this equation. Doing the exact same thing, assuming that only porosity changes, and plugging it into this equation, we get this value, which means that the pressure drop when you reduce porosity by 10% increases by 230% through the media. So that's really staggering. A 10% reduction in porosity really drives up the pressure drop. So it's much more likely that it's age and the subsidence that's correlated with it that is reducing airflow, not the biocover. So that brings us back to the final question. Well, the revised final question: which is better, pipette grade or a Sparger system? And to answer this question, I looked at a few different parameters. The first of which is overhead cost. And typically, Sparger designs are about 30% more expensive when you're just looking at the piping. However, the primary cost with these facilities is typically the concrete. So it is a little bit more expensive to build a Sparger system than a pipette grade. When you're operating it, the electrical tends to be a little bit higher for Sparger than pipette grade. However, the operational expenses are lower. You have to flush the lines less often, spend less time unclogging nozzles. As we saw in the data, the volume of air delivered was actually pretty much the same for both systems. However, the Spargers clogged quite a bit less and distributed oxygen and air much more evenly into the pile. So there are quite a few limitations of this data set. Unfortunately, with COVID and the fact that it's an operational facility, I was not able to get as much data as I would have liked, but I was still able to come to some pretty solid conclusions that were fairly consistent with the data set. Another thing is that before doing this testing, in the weeks leading up, we were getting really torrential rainfall here on the West Coast. And this was probably why we were seeing so much clogging in the facility, as discussed by Tom. As the rain comes down, it pulls the fines through the compost, and those fines build up right above the Spargers or nozzles. And it's like concrete. It'll just build right on top of the inlets and prevent anything from passing through. It also has a strong correlation on the porosity. So there's a lot of great research done, some by Susan McFarlane, on how moisture content changes the airflow through a pile. And typically higher moisture content, lower airflow. We're seeing significant variance in the CFM per cubic yard in the hood versus header data. I have some theories about that, but probably the most obvious one is that in the headers, there's really high airflow that's quite turbulent, so it's hard to get really accurate data there. There's some unaccounted losses through the sides of the piles. When I was doing the hood testing, I was just looking at the tops of the piles and didn't factor in any air that might be going out the sides. The biofilter is not yet installed. Things have been delayed due to COVID, and they're still working on getting the biofilter in place. So a lot of the reversing data is not super significant. However, I hope to go back once they get it installed and gather some more data. It's also a new facility, so there's quite a bit of variance in the way that the controls are operating, and just things are still being fine-tuned. So I wasn't able to do a solid comparison of the finished product or of the temperature readings. I would like to acknowledge Steve Titus and Jeff Grimm for helping, as well as my wonderful coworkers, Jeff Gage, Michael Brown, Jake, and the rest of the team. You guys are great. And here's my works cited.